Okay, today I want to tell you a bit about matrices and where they come from. So I'm just going to start by recapping a bit about vectors, specifically in the plane. So a vector is basically an arrow in the plane. Later we'll deal with vectors in higher dimensional spaces. And the way we encode this arrow is as a pair of numbers, x and y, where x is telling us how far to the right the arrow points and y is telling us how far up it points. So this is x and this is y. In particular, if the vector points to the left, then x is negative, and if the vector points downwards, then y is negative. So I'm just going to draw some vectors. There's one, there's another, there's another, and there's another. And now I'm going to write some column vectors like these numbers x and y over here. I just want you to pause the video for a minute and try and match up one with the other. So I'm going to stick in some red herrings as well. Okay, so I just want you to pause the video for a second and try and figure out which of these four arrows might correspond to which of these pairs of numbers. Okay, so I'm assuming you've done that and have come back. Now I'm going to tell you how it works. So let's start with this one here. This points a certain amount in the x direction, none in the y direction. So it should have something in the x and 0 in the y. And there's only one that fits the bill. It's this one here. So that's the vector 1, 0. Similarly, this guy points directly up, has no x component, so that's going to have to be this one, because it has no x component and 1 in the y direction. What about this one here? This points down and to the left, so that's going to be negative in both entries. So the only possibility is -1, -1. And this one, well, it points to the right and up. And all of these also point to the right and up, so we've got to figure out which of these three it is. Well, you can see it points more to the right than it does up. So the first entry, the top entry, should be bigger than the second entry. So it's not this one. It's not this one. It has to be 2, 1. It points 2 to the right and 1 up. So these guys are not right. So a lot of this module is going to focus on the interplay between algebra on the one hand, like columns of numbers, and geometry, like these pictures of arrows in the plane. So to make the connection to geometry, let's try and figure out, for example, what is the length of this vector. Let's give it a name. Let's call it v. Okay, v is the vector xy. Some people will, try and do something like underline this v or write it in bold. I'm not going to bother. So v is the vector. What is the length of v? So I'm going to move down a bit. I'm going to write the length of v as v with 2 vertical lines around it. Sometimes you might hear me say norm v or length of v. So what is it? Well, by Pythagoras' theorem, it's just the square root of x squared plus y squared, because this guy up here is a right angle triangle. What about this angle here? If we wanted to know what this angle was, we'd use some trigonometry and we'd say the opposite side over the adjacent side is tan of the angle, so this should be arctan or tan inverse of y over x. So you can figure out geometrical quantities of length and angle in terms of these two coordinates, x and y. And conversely, if we wanted x and y in terms of the length of v, the length of this line, and this angle, then we get them again using trigonometry. We get x, it's so adjacent over hypotenuse is the cosine of the angle. So to get x we do norm v cos theta, and to get y that's the opposite, so we do norm v sine theta. Okay, so the vector v it's xy, so it can also be thought of as norm v cos theta, norm v sine theta. Okay, so I wanted to tell you about matrices really rather than vectors. So the way we're going to get there is we're going to ask the question, what happens if I rotate v? So what if I rotate v by, let's say, an angle phi anti-clockwise? Now you just got to get used to the fact that mathematicians like the direction anti-clockwise more than the direction clockwise for some, I guess, historical reasons. So we're going to stick with that convention. So what happens if we rotate v by an angle phi anti-clockwise, so this way? We're going to get a new vector w, and I want to know how to express w in terms of v and this angle phi. So I'm going to get a new page to do that. So let's draw the picture again. So here's v, here's w, this is phi, this is theta. Okay, so when I rotate, I don't change lengths. So rotation preserves lengths. So the length of w, it's a w, is the same as the length of v. And we also know how the angle's changed, right? The angle has gone from being theta to being theta plus phi. So the angle that w makes with the horizontal is theta plus phi. So actually we know what w is, right? It's just by comparison with this formula here, it's going to be length of w times cos of the angle, length of w times sine of the angle. And the angle is theta plus phi. It's this total angle here. And actually we know a little bit more because we know that the length of w is the length of v, so let me change these w's to v's. Now, looking at this expression, we can try and expand these trig functions using the addition formula from trigonometry. So this top entry is going to be what? Norm v cos theta cos phi minus norm v, because norm v is outside the whole thing, times sine theta sine phi. Right, this is the trigonometric addition formula. It expresses cos of a sum in terms of a combination of coses and sines. I'm assuming you've seen things like this in A level or whatever you did before coming to this video. So the second one, the addition formula for sine, I think says sine of theta plus phi is sine theta sine cos phi plus sine phi cos theta. Okay, so this is the trigonometric addition formulae. Now, stare at this for a second. We can see some familiar expressions. So maybe I'll highlight them in red. So this should look familiar. What is this? This is x. Right, remember x was norm v cos theta, and here we have y, norm v sine theta. Similarly on the bottom, we have y and we have x. Yeah, the x is kind of split by this sign, but it's here. Okay, so rewriting this, we have x cos phi minus y sine phi, and then I'm just going to switch the order of these. This is going to be x sine phi plus y cos phi. So this expresses w, this rotated vector, in terms of the original vector and its components x and y, and the angle phi. And it separates out, it allows you to see how the angle dependence and the vector dependence are sort of separate things. So there's actually a very nice way of writing this. And this is, I guess you could say, the main definition of this course. I'm just going to write this as cos phi minus sine phi cos phi in brackets xy. What does this mean? Well, currently it doesn't mean anything. It's just symbols. This guy is the vector v that we started with. This is a 2x2 array of numbers, causes and sines. And such a thing is called a matrix. Let's write it as M. This is a matrix. And when you see an expression like this, you should just think it's a shorthand for exactly what I've written over here. In other words, it's keeping track of the coefficients cos phi minus sine phi, cos phi of x and y in a 2x2 grid in exactly the way they appear in this equation here. So more generally, we define, given a 2x2 grid of numbers a, b, c, d, and a vector x, y, we define the product of this 2x2 thing into the vector to be a new vector, which is ax plus by, a times x, b times y, and then c times x plus d times y. In other words, the numbers a, b, c, d appear in exactly the same way as the coefficients on the right hand side. And you can check if you substitute a, b, c, d as cos minus sine, sine, cos, this expression gives you this formula for the rotated vector for its components. So this defines the action of a matrix on a vector. And the really nice thing about this is it completely separates out the transformation, the rotation that we're doing, and the vector that we started with. Right, so this equation w equals mv is saying you start with v is like a vector, initial vector. This matrix represents a rotation. And we've completely separated out the bit of the rotation that depends on phi, and the bit that depends on, or the bit of the rotated vector that depends on phi, and the bit that depends on the initial vector that we started with. And the fantastic thing is that now we don't have to limit ourselves to rotations. Now we can just use any four numbers, a, b, c, d, and this operation, this matrix multiplication here, defines for us a new vector starting from any initial vector. So a, b, c, d defines a transformation of the plane. Could be a rotation like we've just seen, or you could write down a matrix for reflection or for a shear. All sorts of transformations you can get this way. Defines a transformation of the plane which sends x, y, the vector xy, to ax plus by cx plus dy. In other words, a, b, c, d, x, y. So in the next video we're going to see many examples where I'm just going to pick some numbers a, b, c, d and see what they do geometrically. But just for now I want to tell you a way of remembering this formula here, because I don't know, it's not that bad, but it's going to get worse as these matrices and these vectors get bigger. We're going to need a way of memorizing formulae like this, and I recommend you don't memorize this formula. I recommend you think of it in the following way. So how do we get this top entry here, ax plus by? We work our way across the top column, this is top row, AB, and we work our way down the column of the vector, and we multiply a times x, b times y, and we sum up those results of those things, and we get ax plus by. And to get the bottom entry, we work our way across the bottom row and down the column of the vector, and we do cx plus dy, cx plus dy. So sort of pictorially you should imagine you're working your way along the rows of the matrix, down the columns of the vector, multiplying this by this, this by this, and summing the results, and that's going to give you the corresponding entry of the vector that you output. So you work your way across, this times this, this times this, and you get the second. So that's kind of a mnemonic for matrix multiplication into a vector. And the same thing's going to give us the action of bigger matrices on bigger vectors, and actually it'll give us a way of multiplying matrices together. So, you know, by the time you've finished this module, it should be kind of built into you that you work your way across and down, across and down. It's like sort of muscle memory for your mathematical muscles. Okay, so in the next video we're going to write down some more interesting transformations than just rotations, and investigate some further this relationship between algebra and geometry.